Dzień dobry, guys. Thank you so much for being here. Hopefully, you will excuse that this talk is in English, but Polish is harder than rocket science. So, excuse me, it's in there. So today I'm here to talk about the Fermi paradox and why it's important as humanity that we become a multiplanetary species. So, first of all, I would like to talk. I would like to start with a thought experiment, real quick. I would like to all imagine you. How would you feel if you were locked up, no cell phone, no contact with Earth, no communication with your family, nothing, just you and other 5 crewmates? That's exactly what future humans will need to endure if we want to have a moon colony or a Mars colony. So this is exactly what we do, us, the analog astronauts. The analog astronauts, we prepare to a future mission to any celestial body, moon, Mars, and beyond. But before we go there, of course, we need to practice, right? So this is the point of being an analog astronaut. We do exactly all of an astronaut do, but here on Earth first, as a training. So that's what we do here in Lunares, actually. There's many analog astronauts and also many sites around the world. But me particularly, I got my experience in Lunares, which is in Poland. Many of you are probably surprised that there's a place like this in Poland, but it does. And I want to explain you a little bit of my experience first. What is it? So in this analog site, we have an EVA area, as you can see here. And we have utility rooms. We have many different types of scientific experiments conducted here. But mainly is to test the human factor and also the psychological effects of long-term space missions. So this is all designed for testing this, right? So this is how it looks like. We really take this seriously. We want zero contact with Earth because multiple universities around the world send us their proposals, and we need to have this zero contact. So that's why we have every single of us sleeping pod, and this is how it looks like. It's really cool, actually. And also we have this EVA area when we conduct geological missions, for example, and other type of robotic experiments as well. We do like all types of stuff, right? And many people ask, like, what is the food like? What does an astronaut eat? So this is what we eat. It's not pretty, but it's really important that it's shelf stable, because if it's shelf stable, then it can withstand long periods of like storage. The lunar mission can go for months, of course. So it's really important that the food is shelf stable. It's not pretty, and we are trying to improve day by day the food, but this is some of what we eat. Also, we conduct biological experiments. In my particular mission, what we were doing is we were sprinkling meteorite dust into lettuce sprouts to see if these plants can grow actually in space. So this is some of the experiments. It was a really cool experiment, and we figured out that it's actually possible to grow plants in outer space, in an asteroid, or any terrestrial body is actually possible. And it's really important for any future human colonization of space that we are able to grow food. This is how it looked like. We just have, of course, 2 weeks of growing, but their analog missions, they go for longer, for months, right? But it's a really good first contact with it, and we do just a little of work. There's for sure many other analog sites in the world that do longer and more thorough experiments. But this was my particular mission, and it was really, really, really nice. Why we do this? At the end, this is the final goal, is to have a long-lasting human presence in Mars. If we want to get there, we need to start doing the science first here on Earth. So when we get there, we know how it works, right? And it's something like science fiction. Yes, sounds like science fiction, but what I want to tell you here is, like, there's people actually working on this, and it's not as far-fetched And you might think it's reality and it's happening right now while we speak. There are people already designing, working, and creating the next generation of rockets, of technology that is going to take you to Mars and beyond. So before I go to the main talk, which is the Fermi paradox, I want to just explain you a little bit of my background. I also did this really cool NASA space camp in the US Rocket Center. I highly encourage any of you that is really interested into astronomy, into astrophysics, to check it out because it's a great program. We also did this aviation challenge when we needed to do this different aviation formation. This is like different exercises on the air. Of course, I have a aviation background. I'm also a private pilot, certified private pilot. So it's also something really, really cool, actually, and it helps in your astronaut career. But if something that I want you to take home after this talk is that anyone can go to space. It doesn't matter if you are a pilot, if you are economy, if you are in administration even, it doesn't matter. Any profession can go to space, and I will explain you why in a bit. So another thing that we did here was testing the zero gravity. Again, what an analog astronaut do is testing the environments an astronaut is going to endure on space, but here on Earth. So how do you simulate zero gravity and artificial gravity on Earth? With a swimming pool. So it's not that complicated. So with a swimming pool, you can pretty much have as close as possible this feeling of zero gravity. So that's why it's really, really used around the world. The ESA, NASA use it extensively to train astronauts. And in this program that I was part of, we needed to go to the swimming pool. We needed to build a little structure under there, and we needed to actually train like a real astronaut will do. And this is how the real thing looks. This is Thomas Prescott from France training in the swimming pool that they use to train the astronauts that go to the International Space Station. This is how it looks. So this is a really, really important part for training astronauts. And of course, if we want to get there, we need to practice first. And this is how it looks like. So in real life, actually, they're floating around in space, practicing thousands of hours, one after another, the exercises they're going to do there. If they do it there once, they already practiced it here on Earth a million times. So that's a part of the training. Another thing that we did in this NASA program that I mentioned is it was actually really fun. It was the zero G and the gyroscope. Gyroscope machine, when you can simulate the Gs that you get during a takeoff. In this machine, you can get up to 4 Gs, 5 Gs, but during a takeoff, the astronauts can experience up to 9 Gs of acceleration, which is a lot because you can feel all the blood in your head just go to one side, and it's just not good. It doesn't feel that good, but it's just something that you need to get trained for, and that's something that astronauts that go to space need to also get trained for. And finally, the last part of this project that I was doing at NASA, we conducted a challenge because it was not just training as an astronaut, it was also doing real science, doing a challenge. So the challenge of that year was developing compliant mechanism. And in this compliant mechanism, you need to have something that it doesn't have mobile parts, right? Like something to solve a problem in space. So what my team and I come up with an artificial muscle that expands and contracts when you apply certain temperature to it. We have this idea of maybe we can use it for next generation exoskeletons, maybe, or it has like 100 different applications, but this is one of the projects I just want to show you real quick. So that's a little bit of my background. But what I'm here to tell you about is the Fermi paradox. And I think it's something really, really fascinating for me. And I think in these times of instability in the world, I think is really, really important to share. So it will make sense in a minute. Just hold with me here. The Fermi paradox is something really simple. It's a question. It's where is everyone? That's the whole paradox. So I'm just gonna start with some crazy numbers here. Please bear with me. There are 100 billion stars in the Milky Way galaxy alone. That stars have at least one planet each. Some of them have more. So just do the simple math, and there are a lot of exoplanets. And every single of that exoplanet can have water on its surface, just if it's in the habitable zone, right? So there are some planets that they are too hot or too cold. So those, as long as modern science know, there's no life possible if there's no water, right? So still with this, let's say, mm, parameter, still there are millions and millions of planets just in the Milky Way galaxy alone that can harbor life, right? So it's something that we would like to think about in this graph, which is something as a time scale of the universe, which is the universe is 13 billion years old. Just imagine that number for a little bit. It's a lot, but you can think in just 13. Just think in your number 13, 13 billion years. And the Earth is 4.5 billion years old. So you have 9 billion years that you have all this time, like all these planets, all these galaxies have all this time to develop life, right? Nothing is stopping them. The laws of physics are the same everywhere. So the possibilities of somewhere else, another planet outside of the Milky Way, on the Milky Way, to develop life, they are quite high. So there are literally thousands of them that can harbor life. But the question again of the Fermi paradox is, where are they? Where, if the universe should be teeming with life, where are the starships all over the place we should be seeing on the night sky, right? There's something in the Fermi paradox that is called the great filter. The great filter has many answers. So there's something that we still not sure what is stopping all these civilizations, all this life, to reach spacefaring capabilities like us. We humans, we are a civilization with spacefaring capabilities because we can launch rockets to space and reach it. So if there's all this sheer number of planets that can develop life, and they have 9 billion years to do so, then we're all there. Where is everyone? That is the Fermi paradox. So I really like to think, and not just me, like the whole scientific community, there's just three possible answers to the Fermi paradox, which is the first one, which is the most boring one, is like we are alone. We are just one of, if not the first civilizations, at least in our Milky Way galaxy, which then I think is to cherish our planet and to see how rare Earth is. Earth is a cosmic impossibility. The other question and the other answer to the Fermi paradox is like, then the distances are too big to have communication with other civilizations. And the third one will be that is just life is way much rare than we think. So going back to this Fermi paradox answer is the point that Earth is really special. I show you the numbers. I show you the possibilities. Then, and still, we just know that Earth is the only planet to have life in the universe. So far, maybe there's another ones for sure, but so far, Earth is the only place in the whole universe that we know there's life. It's a really special planet we don't really think about because we live here all our lives, but a lot of possibilities need to come together for Earth to exist, which is a strong magnetic field that is protecting us from the photons from the sun. It's not too close to the sun, not too far away. It has a rocky surface, and most important of all, life evolved and developed here and had a civilization. And going back to the filters of the Fermi paradox, right now we're in a crucial point in human civilization because we have the power to destroy ourselves right now. We have nuclear weapons. So for me, it's really important, and not just for me, many scientists, many entrepreneurials, they really think we should become a multiplanetary species as soon as possible because we all have the eggs in one basket. We just have one planet. If we become a multiplanetary species, there will be much more room to grow, much more room to expand, much more room to develop new technologies. Like for sure, I'm sure you heard about SpaceX Mars plans to colonize it. Also, Elon Musk plans to go out there. They are not far-fetched. They are working right now. Last year, and actually, I think yesterday, Starship in the US was launched. So it's actively happening. There are many destinations, which is the moons of Saturn, Venus, Moon, the Mars, you name it. The thing is, we need to become multiplanetary. And it's not that far-fetched as you might think. What I want you to take from this talk is like, it's not just happening in the US. This is happening in the US for sure. The Inspiration 4 crew, these guys, they are not even astronauts or pilots. They are a doctor, they are a businessman, they're a nurse, and it's just a teacher from geology. So they can come from all types of people. The International Space Station, for example, it costs 150 billion US. Sounds a lot, yes, but it was made thanks to the cooperation of many nations. So it's not just one nation. We need to work all together. And if we work all together, we can achieve multiplanetary status for sure. And going back to Poland, where we are, it's not just the US. That's what I want you to take from it. We have the first Polish astronaut in 1978. Excuse me if I'm not pronouncing this right, Mirosław Hermaszewski, and the next astronaut, which is going to be Sławosz Usznanski, maybe in 2024, 2025, he's already part of the ESA. So it's completely doable, guys. Like Poland has demonstrated many times that has a lot of potential into the space industry. Where is the next European SpaceX also? Like, you guys have a lot of young students with a lot of potential. Like, I met many brilliant scientists here in Poland, and I really think a European SpaceX is really possible as well. Here in the ESA, in Europe, sorry, you have the European Space Agency, you have Arianespace. There are many, many options in Europe, and I think it's just going to grow. And I just want to close with this. We are in a crucial moment in human history, in my opinion, in human civilization, because we are in this moment of the Fermi paradox that we have the power to destroy ourselves. Maybe that's the filter. Maybe that's why all these other civilizations didn't make it this far, because as long as they have the power to destroy themselves, they do it, right? So we need to decide which type of future do we have. We want a cyberpunk future or we want a solarpunk future? We have the same technology. It's just a matter of deciding which type of future we want. And I just want to close with this slide. Many astronauts that have been to the International Space Station, they have described this overview effect, they call it, which is once they see Earth from above, they don't see any borders at all. They just see one planet. Do you see any borders here? There are none. So I think if we all work together and we forget about borders, I think border is the worst invention of human history. We can all reach multiplanetary status because we are just one planet. Thank you so much.